Okay. Everybody give me a green light so I know you're alive and well. Okay, there's a couple people not responding there. It's important when we do participation things that you participate, because if you're not marked as here, you know, the little algorithm we have that marks attendance, it doesn't, you could be here at 4 o'clock in the afternoon sitting in your chair, but it doesn't start counting your attendance until exactly 6. And then I hit a little button here when I consider class over, and that's when it stops timing you. So I know some people, they get on and they come on a Tuesday night thinking they're going to have to log in some extra hours, and then I'll never notice. Well, I don't even have to notice because the grading algorithm takes care of that for me. Okay. Let's see. I did not log on as a student tonight, so I'm not among the list. So I should have 25 people in the list, and we got 22. So we're missing 3 people. I hope they're okay. Hopefully they'll show up. Let us look at the syllabus, make sure we're on track with where we need to be. I think we're in Unit 10. Yes, we are. We're going to talk about counters and shift registers tonight in anticipation of these 2 sessions, both of which are very practical and very good, and probably something you're not going to find where people are generally this well prepared. If you've been paying attention, when we get here, they'll just make a lot of sense to you. And you'll suddenly have something in hand that seems like a very, very practical tool. And we couldn't get here without doing all the other stuff first, but tonight we'll talk about counters and shift registers, which are basically the same thing as digital components, except they're for sequential logic. We introduced sequential logic last time, well, actually 2 sessions ago, and talked a little bit about latches and flip-flops. We'll finish that up and then talk about counters and shift registers. I know I left you with a kind of floating assignment about a flip-flop and some analysis on it where we were not using a capacitor, but nevertheless we were going to get an edge, so we could consider that flip-flop to be an edge-triggered device and actually call it a flip-flop and not a latch. Remember that. If I call it a latch, unless I'm just happen to be being goofy at the moment, if I call it a latch, I mean level clocked. If I call it a flip-flop, I mean it's edge-triggered. And if it's edge-triggered in any way, and that could be by way of as the MS flip-flop does, it could be by virtue of the fact that it has 2 stages to it which are clocked in opposite directions, causing a kind of an intermediate edge. And we'll look at that in a second. So let me look up my where we left off piece of paper for this class, because they're a little different than the other class. They have fewer people, so they get a little bit ahead of you sometimes, because the in-class stuff, by the time we've cycled around all of them and the calling on people thing, I don't want to hear their voices again for a while. And so I don't necessarily do all the exercises. Okay, so let's talk about the difference between level and edge clocking. I think I'll do it with one of these guys.
Professor, real quick before we start, for the selfie you asked from last class, do you have a due date for that? I mean, I just submitted it like 10 minutes ago.
It has to be in before the test.
Okay. Right.
So, I mean, if you submit it 10 minutes ago, that's fine. I'm not in any rush to get them. And matter of fact, I think I've gotten some. And I looked at one. I didn't even know who sent it. So just if you want extra credit for that, do it, because it makes the attendance thing that I look at over here be a lot less boring if I see who the person and the name are together.
Gotcha.
But yeah, if you just send it in, I'll have gotten it. I'll see it tonight because the people that do my email probably won't be in the office until 9 o'clock tomorrow morning, maybe 8 o'clock. But then I'll see it.
Professor?
Yes.
The one you couldn't see, was that through Blackboard? Or was that sent through email?
No, I haven't even looked to see them.
Okay.
Yeah, I just haven't paid any attention yet. I'll be looking, sometime this week because I'll want to update the pictures inside of the attendance thing. So the sooner you send them to me, the better. Or if you never send me one, that's okay too. That won't count as extra credit for you, but that's fine. I mean, who cares? It's just I'm using it to make the thing that I look at when I see your names be, version 2, more enhanced. It's got a picture of you there, and instead of just this cold name that I have to look at turning around over the day. Okay, so let's talk about level clocking versus edge clocking. We talked first place about what a clock could be. And we said a clock is really any signal that controls when another set of signals take place. So if I were to simply have a signal that did this and never did another thing again, but on that particular edge, or it could be this edge, or it could be on that level, something happened in the system. That was a clock for that event. Clocks don't have to be periodic like they are if we think about the clock on the wall. They just simply have to provide the ability to synchronize things together at a particular point in time. Now, we talked about, when we were talking about the various types of latches and flip-flops, we had some which were just basically transparent, where the data causes something to happen immediately being, propagation delay time in the future, but they didn't use a clock. Particularly in the case of the D latch, we found in order to make it useful at all, we had to stick a clock in the way to make it be transparent only when the clock was high. Now, it might be low. We could be using a clock which goes the other way. There's nothing that says a valid clock couldn't go down instead of up, and we could be synchronized with this leading edge. As a matter of fact, if we think about this signal here being clock, we could think of the other signal as being called not clock. And if both are broadcast at the same time, these edges will be relatively close to the same period of time. They may be at different times because of various propagation delays, perhaps in an inverter or something like that. But the point in time with which we're interested will be some number of nanoseconds around that particular point right there. But this is still a clock. Now, being transparent means that while the clock is in its asserted state, for example, while it's high, we're going to allow the signal that's being controlled to pass through to the outputs. Now, that's not a good thing necessarily. But if we were to simply say, well, we've got a D flip-flop here, I won't draw it formally yet, and we have a Q output over here. If we put a clock on this thing, which is level triggered, then during the time the clock is high, as this moves around, this follows the motion. So even to make a D latch, and this is a latch because it uses level clocking, to make this even remotely useful, we would want to ensure that this D signal only changed while the clock was low. That way, the entire time that it's high, we'll see the correct value, and basically that'll be the value that gets latched into Q at the end of that high period, basically after we're not high any longer. So we would want D to change in most applications when it's not going to be directly visible by Q. We would then want to hold it stable during the entire time that D is raised or asserted so that it didn't change, and we're assured of that when it falls again to become low again. When it's low, of course, we could start changing D again. Now, unless we were to see one of these level clock periods, D would never make it through to Q. And as I mentioned earlier, if D is dancing around while it's high, whatever value it has when it drops is going to be the value that gets latched into Q. And we may have no control over that because the actual exact moment in time it's going to drop is not well known in the system. I mean, we have an approximate idea of when it's going to be, but two different pieces of hardware, two different D flip-flops may do it slightly differently. The timing may be slightly different. So what we want to think of is when we assert a clock, when we say we assert a clock, what we're saying is the same as asserting a signal. It's when the signal is providing some value to the system. The rest of the time it's kind of idling. We don't care about that time. Of course, the inverse of this clock could be the main clock and could be useful. We could say that for our purposes, we only want the D signal to pass through while the clock is low. Maybe we have more control about being able to hold it still while the clock is low. And we may have other reasons why we may want to use one over the other. Anybody have any questions about level clocking? Okay. Let's talk about edge clocking now. In a way, when this clock drops, we're actually doing the latching event, right? That's when the latch occurs. And that is truly the low dropping edge of a clock. So the actual latching does occur on an edge. However, the difference between a level clock and an edge clock is the amount of time that it's allowed to stay asserted. A normal edge clock will look like this. Basically, there is a tiny bit of time between the up and the down, but it's in the very low nanosecond range. We're still going to latch it in effectively on the dropping clock of the spike. But the dropping clock is so close to the rising clock, and this is a rising signal, we would still call this a rising edge clock. So it's asserted only during that one little tiny period of time there. If I zoom way in on it, now look at that, it looks almost the same. It's just a very short period of time that it's high. But because it's doing the blocking while it's high, while it's low, when it's high and it's allowing the data, it's enabled, then the data, if it actually changed in that little window right there, we would see the last change when it dropped. But because this is a clock that goes up, we call it a rising edge clock. Now, if the signal were normally high, but we allowed it to drop and come back up, this is a falling edge clock. I'll just write fall here, and you'll remember it's falling. So a falling edge clock. Here's the zero baseline down here, just like this was the zero baseline for this guy. But sometimes the clock is held at a higher level, and when we want to capture a piece of data or we want the clock to function, we lower it and bring it high again immediately. Now, the way we accomplish that in our circuit was we simply allow a level clock to pass into a capacitor and a resistor arranged in what we would call a high-pass filter way. Now, we don't have time in here to talk about what it means to be high pass and low pass and all those sorts of things, or even why the clock edge would have, high signals in it as opposed to low signals. Just really quick on that is a guy named Fourier identified a property of repeated waves, and can also be looking at a single signal, to say that repeating waves really consist of sine waves and cosine waves of different frequencies added up. It turns out that if we took all the odd numbered frequencies and we alternated subtract and added them up while decreasing their amplitudes, ultimately you get something that looks like a square wave. It becomes more and more square the higher the frequencies that are in it. So what we're basically trying to do with this circuit that we build here is we're trying to grab only the high frequency stuff, because most of them are based on these two lines right here. Most of this other stuff has to do with the main frequency of the signal. But if we could grab these high frequency signals that are making up these two edges here, then we'd be able to present them as output signal. And that's exactly what this high-pass filter configuration does. Out of this, on this side of the capacitor, we're going to see a signal going up. I'm drawing it on the wire here, and then a signal going down. But because this signal is relative to ground, we'll only see the rising period. We'll see it every time there's a rising event here. We'll see one of these pulses over here. And if we use this as the clock for a flip-flop, then we're truly using just this little tiny edge piece or level piece right there, which is on the edge, in order to capture the signal, which is exactly what we need to do. Now, when we are talking about flip-flops in general, the notion of a latch is a great one to have in mind. Almost all the flip-flops we have are based on something that has a latch embedded in it. If you remember initially, we had either an SR or an RS latch, depending on how you want to name it, which we put a clock on, but then the engineers got a hold of it and they tied R and S together and renamed them to D. And then we put a clock on it. And then we put an edge-triggered clock on it, which turned it into a flip-flop. I may not have showed you the intermediate step there, but by the time we got to here, we were a flip-flop. At that point in time, the engineers got a hold of it again, and they pulled the D back apart again and labeled it J and K. J and K served useful purposes because they added a fourth function. Remember, in an RS and a D flip-flop, if we have a table, an RS flip-flop can basically, if it's 0, 0 as its inputs, that's assuming this is reset and this is set, it causes no change at Q. If reset is 0 but set is 1, it causes Q to become a 1. If reset is a 1 and set is a 0, it becomes Q to be a 0. And if it's a 1 and a 1, it's disallowed. We can't do that. That's no good. So this state is just, you don't allow that. Which is what the engineers took advantage of to create the D flip-flop, because they recognized that unless you need this don't change state, we can just use these center two values here by tying R and S together, one of them through an inverter as D, and we can get the two center things to occur. Now, D without a clock, of course, since we don't have this state, is useless. Just adding a normal clock like this, level clock, means D can change the entire time it's high, and we call that a transparent D latch. The engineers, we talked to them, and they arranged to cause that to be differentiated by the capacitor, and then we changed it to edge-triggered, and now it became a truly useful flip-flop. One of the most common flip-flops you're going to see in use is a D flip-flop. It has to be edge-triggered. I'll just put an E for edged. And it's on the high-going edge, and it will almost always have either or both of preset or clear, and both of them will be negative going signals normally. So this is the most common D flip-flop we would encounter. An example would be something like the SN, what would it be, 7474. P chip, or it might be putting N. We could put an N or a P. I'd put P out there and make it plastic dip. But this particular TTL chip would do this function for us quite well. Now, they saw in this case the fact that if we uncoupled it, that case didn't have the clock, even though the clock is going to still be useful to a JK. Turns out that we really just did all that tying together to avoid ever having that state. So if we untied them, we can't call them RS because they're no longer RS. They have new names. They have name J and K. We add a fourth state, which instead of no change, set it to 1, set it to 0, the fourth state turns out to be toggle. So on every clock it receives, and for JKs, we want the clocks to be edge triggered. We want to see Q change to whatever Q wasn't. So Q and not Q will flip-flop back and forth. Part of the name flip-flop comes from that. But if it had a level clock, which would have been here, or the JK, we call the flip-flop, I'm sorry, edge clock. If it had a level clock, as this did or as the RS might have, we would call it a latch. So JK often has a preset and clear as well. And the only main difference between it and the D in terms of what you would actually go out and buy is the fact that the JK has this toggle function. However, this right here, this part, is very expensive relative to other techniques of putting a level to edge converter on a chip. So this JK, which uses the actual edge, is normally, more commonly, put into a JK, we'll abbreviate so we're not tacky here, MS flip-flop. Now it, in fact, is using level clocking, but it's arranged them in a way that we're ourselves in the chip not using those levels. Instead, we're using the edge between the two levels. And that's going to make this a much more cheap, a more common chip. So a JK master slave flip-flop with the preset and clear, again, normally going low, is going to be the chip you're most likely to run into. It will actually have what appears to be edge triggering, most often on a falling edge. Now, the pictures of it, we'd use schematics of it, very often will not show this correctly. And it's just traditional that we just know what this chip does. So sometimes we let them slide a little in the schematics. But what you would really imagine it to do, if you were showing what the clock itself is doing, is it would show you an inverted signal. But because it's a two-stage clock, the actual external pin maybe shouldn't be labeled that way. Because in one case, it is triggering something that happens on a falling edge sometime later. But on the other hand, the actual clock it's changing is a level-triggered high-going clock. So we actually have to look at the diagram I gave you to study and see if we can understand what's going on with that. Does anybody have any questions thus far? I should take a sip of my coffee, which is either coffee or coffee pot cleaner. I'm not sure which. You'll find out shortly. Nope, can't tell. Anybody have any questions? Okay. Let me, for the moment, grab this guy. And we'll look at him for a second. He is the D flip-flop we were talking about earlier. Most common when you're going to come into, except for this particular one does not have the preset and clear drawn on it. But it does have a very proper clock. So if we think about how this is working, the value of D here is given to the two blocking AND gates, and it's given to them in its D form and also in its inverted form. So we're guaranteed that these are always opposite, which is exactly what we want on this, because if you recognize this is simply a latch, and the latch has a clock in front of it, and the clock itself is triggered by R and S, but R and S don't appear until, let's pretend I may have them backwards with the labeling of the chip, but let's pretend like that's reset and that's set. This is set and reset even though D is still this signal here. This is not D down here. But as far as what's passing through to the next gate, this might be R prime and S prime because they only appear during the high part of the clock. That one little point in time way up there. Then the signal passes, and of course that gets latched in because that's what this thing does if the two are different, depending on whether it's set or reset. Now I may have labeled it backwards. These could be set and those could be reset. It also, because this is a NAND function, may be creating the signal by virtue of it dropping as opposed to by virtue of it rising. But we know that from looking at the latches on a different day. So here we have our differentiator. So the pieces of this that we would care about are this part out here is a simple latch. Almost all flip-flops and latches will have this somewhere in the picture. If this were not clocked, if it were simply hooked through straight to D, whatever D is would pass through straight to Q. It'd be a transparent latch at that point if there was no clock. But because we put these, and these are operating like blocking AND gates, yes, they're NANDs, but it doesn't matter. We're still blocking with an AND function. And what are we blocking? Well, we're blocking D and not D anytime the clock isn't high, because these ANDs or NANDs cannot function as their main purpose until this is a 1, right? If this is a 1 and that's a 1, that basically says this gate can work. And you think of it as an AND. Get rid of that bubble there. Get rid of that bubble there. So it's just an AND going into half an OR. Bubble goes away. Bubble goes away. So it's just an AND. And we know we can block signals by making one part of an AND a 0. But the clock raises them both to 1 for an instant in time. And at that point, whatever D and not D are, and they have to be opposite, will be seen over here by the latch. And of course, the latch will immediately act on it. This inverter, we talked about why it's in the picture. It's there to make sure that D and its inverse are available in the signal. And we talked about this as being the differentiator or the high-pass filter that's taking care of turning this wave here into those two pulses there. Remember, the low-going pulse is basically clipped away because we don't allow in this circuit any signals to go below ground. And this signal would go above ground and then below ground, above on the rising edge, below on the falling, because that's what's happening. It's moving from 0, no change, into an upward direction. No change, then boom. So the fact it's low in the middle, low in the middle, low in the end means didn't change, didn't change, didn't change. So it's emphasizing only the point in time when there's change. That's what derivatives do, isn't it? You guys that took calculus already are going, you're cheering. You're waving pennants and all sorts of stuff for that, because now you know why it does it. But rate of change is a very important thing in electronics, both this direction and also the other way when we treat it like a low-pass filter and we do integration with a capacitor. Okay, so this is a popular chip. We could go out and buy one of these, but more than likely we would add in here, before the latch, some additional asynchronous circuitry to handle preset and clear, which would override the clock logic. I just didn't have a picture of that handy. Now the JK that we were talking about, let me find him, looks like this. We have coming into the main clock signal a rectangular signal. The amount of time it's high is when we're going to take and make the latches in the system enabled, at least the ones that are in the sphere of influence of this particular clock. Now, we have two parts to this. We're going to call them M and S, because this is MS flip-flop. And what we're going to do is we're going to treat these three input AND gates the same way we did in the last picture. We're going to block the signal of either J or this other wire by making this be a 0 while the clock is low. So if there's a 0 here and there's a 0 here, it doesn't matter what J and K are doing, and it doesn't matter what these two feedback signals are. Notice that the feedback is simply Q on this side and not Q on the other side. They're going to be why we get things ultimately to be able to toggle, because we're passing them to the other side of the flip-flop. The main first stage of this flip-flop is separated right about there. So this works just like a latch. It happens to have J and K, and we've said that J and K are going to have multiple functions here. First of all, if J and K are zeros, we've really made it super so this thing can't do anything even if the clock goes to a 1, which it will, right? So if J and K are both zeros, it doesn't matter what the clock is doing. These guys are off. They can't pass any data. Now, if we set J to a 1, I'm not sorry, I'm doing the clock there. We set J to a 1, then depending on the clock, this may or may not be able to do anything. Well, if not Q happens to be a 1 at the moment, then that means J, which is going to mean set Q to a 1, should be able to pass through. Because on the high clock, all three of them would be a 1. And it's saying, no, we'll forget about the inversions for now. Just this is an AND feeding half an OR. Okay, so if it's a 1 and this guy's a 0, because if this is a 0, we're still in the same state of this guy here can't do anything. If this turned out that the thing being fed back, Q is already a 0, then setting this to a 1 does no harm. It won't pass through any signal because Q is already a 1. And the same thing would happen on this side. That if all of these guys are zeros, let me, let's work. So if the clock is low, oops, clock is low, and J is low, it really doesn't matter what, the not Q signal is doing because it won't get through. However, if we've raised K to a 1 and Q is currently a 1, meaning that Q is set, we're getting ready to try to reset it, that means this will be a 1. When the clock goes high, the net result goes up, which is a 0 here, but it gets doubly inverted, so we don't care. But the 3 1s mean that the signal passes. So it's now setting itself up to set for a reset. If, of course, this guy feeding back from Q had been a 0 to start with, meaning it's already reset, nothing would have changed over here because we don't have 3 1s to pass a signal through. So we've looked at the cases both are zeros, either one is a 1. What happens if J and K are both 1s? Well, if they're both 1s and the clock is low, then one of these two will be high. Let's say Q is high at the moment. If Q is high, when the clock goes high, that will pass through. This guy, of course, won't be enabled even when he goes high because not Q is a 0. And so it will cause the toggle, and of course the same thing would happen on the other side. So setting J and K caused this latch right here to grab the correct value, either J or K, to be passed on to Q or not Q, or 0, 0, which means do nothing, meaning they're going to leave it set as it used to be, never, not even change it, or to give the inverse of whatever Q and not Q were. That all happened just as this clock fell. We're making the assumption we set J and K up way back over here somewhere. Clock went high. We got a falling edge. Now, that may not be exactly what's going to happen here, right? We said we want the clock to go high and pass the signal and do the latch. What if the clock is doing this here? What's the clock doing over here? Well, the clock over here is dropping and then rising. So this inverter is creating basically the same clock as this in its inversion. We'll call it not clock. But this stuff right here is another latch. So from that point on, we have another latch ready to latch something in. Well, what in the world is it going to latch in? Well, it's going to latch in the output of this latch. If this guy says set, that'll be latched into Q. If it says reset, it'll be latched into not Q. If they're both on, it'll cause it to toggle. If they're both off, it'll cause it to do nothing with its current data. Remember, it's storing its data, which are Q and not Q here. This guy is storing basically set and reset inputs for the next stage. Since we know latches are generally, if they're clocked with level clocking, this makes the perfect level clock because it's going to block while it's low, and it's going to, as it goes high right here, latch whatever S and R are. But that's exactly the same time as this guy latched its J and K into S and R, delayed only by a little bit because of this inverter. So that means the only time we can latch anything from this stage into that stage is on the falling edge of this clock, which is the rising edge of this clock. Changing signals either while it's high here or low here will never affect anything past this clock. So we effectively have created an edge clock. When clock drops, it's the rising edge of the not clock, so it's basically a low-going edge that's created by virtue of these two clock signals, and it only works because there's a small delay. By the time the signals are stable here to be gotten, this clock will rise and snatch it in and become the thing that gets transferred over to the latch on this side. So that's a fairly crafty way of getting that to work. Nowhere in there did we need a capacitor. We didn't need to do it. We simply created a moment in time where we have that little sliver of I'm high and you're low, and we reverse it. And because of that, we can only snag things while on both of them the signal is high, but it's so small a time when they're presenting the correct signal that it works effectively the same as having done an edge trigger. Anybody have any questions about that? Okay, so if you were given a, I don't know, a cracker, a paper clip, and a season's episodes of MacGyver, you could explain that to me again? Okay, I see a lot of you smiling. That's good. Smiling is good. Okay. This guy you need to kind of understand, but it's really quite simple if you just go through step by step by step and you recognize the parts. That's clearly a latch. That's clearly a latch. This is clearly that configuration of blocking something with a AND gate. Same thing here, just happens to have 3 inputs, oh well. And we notice the inversion happening here, and we would realize that this signal and that signal, if I were just to draw the other signal, it would look like the same signal here. But since we're actually snagging in the first case here and snagging in the second case here, it doesn't need much of a delay between this and this in order for that to occur. And of course, the chip is engineered to make that happen. There may even be some additional propagation delay built into that internal inverter. Okay, let me move along here. Okay, we have been talking when we draw circuits about schematic diagrams, and we've had some symbols that we've learned. Let's review some of those so if you were to encounter them somewhere along the way, you wouldn't be in great distress over it. So, make sure that's what I want to do next. It is indeed. Jemana, what is that a schematic symbol for?
Is it like relative to ground?
Right, that's the ground symbol, that's right. Okay, Oscar, what is this a schematic symbol for?
That's like a battery.
Yeah, that's right. Good, good,
Yeah.
good, good. Okay. William, what is that a schematic symbol for?
A resistor.
Yeah, yeah. Might have a circle around it, might have some extra wire on it. Noah?
Saturation.
Simon Blemo? I'll draw the circle around it and make it a little easier to look at.
Yes, that isn't a simple
Yeah, what? Robert?
inverter.
Robert, what do you think that is?
Transistor.
This was a resistor here.
No transistor.
Transistor, okay, yeah. Okay. Kyle?
I don't recognize that one.
Okay. Alexander?
Capacitor?
A capacitor, yeah. Tatiana? Rajana?
Is that a battery?
This was a battery over here.
Oh, is that also a capacitor then?
But what type?
A polarized?
Exactly. Good job. Real good job. Gabriel? Basanti?
I'm not sure.
Thomas? Patel? Thomas?
Is it a light emitting diode?
Yep, that's a light emitting diode. Now, did I miss any symbols that we've commonly been using? I might have used a switch, which would look like that. Maybe, maybe not. Some classes I do, some classes I don't. I think that's most of the components we've covered. We did see inside of our 555 timer some schematic symbols that were unfamiliar to us, but let's review a couple of the other ones first.
I think you missed wire.
I did miss wire. Here's a piece of wire. Woo. Okay, that's a nice piece of wire also. Okay, this one here, Ryan.
I struggle with remembering names, but I know what it does. It's that someone said gate in chat.
Yeah. Yeah, don't cheat.
It just popped up.
Yeah, I know. You don't be staring. I'm not saying you cheat. I'm saying the guy that's putting the answers there. Remember, as a student, I could get everywhere I need to be, you know, so I sometimes see chats you don't think I see. Rashana, tell me what this one is. Second one.
Is that a NAND gate?
Yep, and the
Or
first
NOR?
one.
NOR.
What was the first? So this is
First
an
one.
AND.
Oh, that's an AND. Yeah, that's an AND.
Okay, and this is?
A NAND gate.
That's right. Okay. Yeah, I was on Discord the other day watching some chatting going on, and it was most distressing. You got to do your own work. So this is an AND, this is an AND, this is an OR. That's an OR. However, we have two others we need to know. That's the other picture of an AND. And this is another picture of a NOR gate. Remember, the De Morgan form this looks like an OR, this looks like an AND. Looks like an AND, that looks like an OR. Bubbles are on the input, not the output when we deal with these. We also talked about a simple set here. The buffer, and the inverter. Of course, we said there's a second picture of an inverter we can draw, and sometimes will to make things clearer. Oops, I have no bubble on its nose. And then we saw inside of the 555 timer we saw a gate that looked like that. This particular one that we saw is from the family called op-amp. And specifically, this is a comparator. I hook two voltages up to the inputs. The inversion here means it does a subtraction of this voltage from that voltage. And as a comparator, if the answer goes negative, this will swing to its lowest value. If the result of subtracting them is even remotely positive, meaning this guy is bigger than this guy, it'll swing to its highest voltage. So while an operational amplifier is in fact a linear circuit, meaning it's normally not used in digital circuits directly, when it's used as a comparator, it's able to perform a digital function. It will either be all the way high or all the way low. They might ask what happens if they're exactly the same. They never will be. You just can't do that with one of these things. But if you did, it would be even the slightest off, it would jump all the way to one or two of the other voltages. Internally inside the 555, we saw a transistor. We saw a different picture of a resistor, which looked like this, just a little square box. We saw a RS flip-flop. We're going to talk about how they might be designed. And most of the rest of it was simple wiring that goes on inside there because a lot of that chip is external. So these are the things that we have looked at and have some understanding of. But now we need a set of schematics for the flip-flops and latches we've been talking about. Raul, you have a question?
Yeah, we also, I don't think I see it there. We also went over XOR gates, right?
We did. XOR gate look like this. We also almost immediately figured out how to build one with NANDs, but yes, we do see these. We also see the XNOR, which is simply the same thing as that with a bubble on its nose. Yes, those would be the ones we've done. Okay. Okay, I was looking at something on the other screen there for a second, sorry. Notice we have 24 attendees now. The worst, not the worst, the biggest that number can get is 25, so somebody's not here. Wonder who. We'll have to see later. Okay, so let's go over the rules for doing the schematics for flip-flops and latches. First of all, we're going to draw a box. I've been calling a lot of element boxes. Eventually, boxes will normally mean units of work type of thing. They are function units of function. And quite often, boxes will be hooked to a data bus or an address bus or both. And just kind of remember that's kind of my slang term for things that are doing that type of function. But the box generally has the following features. Its outputs will appear on the right-hand side. If there's a Q, it's normally at the top. If there's a not Q, it's normally at the bottom. You might have one of them missing. You might have both. But that's where they'll normally live. Now, everything I draw can be flipped 180 degrees in some pictures depending on what they're doing. For example, if we're building a counter that has to pass the bits to the left, normally we'll flip it over rather than leave it exactly as I'm drawing it here. Okay, on this side, we have the input signals. If it's an RS latch, RNS will appear possibly in the other order, with S on top, R on the bottom. If it's a D latch, B will normally appear at the top. The JK, J will normally be at the top, K will be at the bottom, and the clock will appear between them. If the clock just comes in and butts into the chip itself, that's a level clock. As a matter of fact, it's level on the high signal, so it's a positive clock, a high signal clock. If it's and so it would be active when this is active, if this is the clock here. And usually it'll be labeled on the chip as clock. Okay. If it's on the low edge, or low level, like here, there'll be an extra bubble right there. Except, as I mentioned earlier, in the case of JK flip-flops, all bets are off on how the clock will look. It's to be assumed, unless you're told otherwise, it's probably an MS flip-flop, and you should assume it's a low-going, what appears to be edge-triggered clock on the second stage. Now, if what we have is edge-triggered, except for the oddball case of a JKMS, there'll be a little triangle drawn here. The triangle implies edge-triggered, and it's edge-triggered on the rising edge. If we put a bubble here, it's triggered, edge-triggered on the falling edge. If you have other signals, like preset or set, those are typical names, or clear or reset, the asynchronous signals normally will appear on the top or bottom, though they may appear other places. This is normally the way they'll schematically be drawn. And they very often are low-going signals. Sometimes you will see an invert here. Now, whether or not that's correct or not, because it's not really the inversion of not Q. Some manufacturers show it that way to indicate to you. So that may or may not be indicated correctly. But we can tell from the labeling that this is Q and that's not Q. It's not the inversion of not Q. Okay. So let's put an example up here and get you to tell me about it. Okay, now try to do this on your own. Don't use the chat to tell everybody the answers because they don't learn anything. And then when the test comes along, they got to do it by themselves because the chat will be fairly useless then. Raul, tell me about this one. What type of flip-flop is that? And what's the characteristics?
Sorry,
Well, it might be a latch. Might be a latch. Okay, well, let me give it.
Sorry, is that like a NAND? Hold on. Sorry, I'm not 100% sure.
Okay, well, let me do one here. We know it's got to be a flip-flop. It's got edge triggering. Okay. Edge triggered, going edge. So we know that if we have a clock whooping along like this, the thing's going to actually be triggered on that falling edge, on the next falling edge. That's the only places it's going to be triggered. It happens to be a D flip-flop. So it's an edge-triggered D flip-flop, triggered on the falling edge, with an asynchronous reset. We don't need to mention the fact that it's low going because that's almost implied, but we would look at the schematic to make sure. And it only has a Q output. It does not have the inverted Q. So we could fairly well characterize that. If that's what we needed in our circuit, we could go find that and we could buy that. Let's do another one here. Okay, Robert, why don't you tell me about that one?
Would that be a D latch?
I should actually write clock here, so but I don't need to. You all are aware of that. Same thing, I should have written clock up. Okay, specifically, what type of D latch?
Um, I'm not sure.
Okay, I got dogs coming after you there. I can hear him barking away. What's his name or her name?
Shayla.
Okay. Okay, so this is a D latch, just as he said, and it is clocked. What type of clocking? It's clocked on the high level. So it's a level clock D latch, meaning it's transparent when the clock is high. Okay, do one more of these and then we'll be on to our next adventure here. Actually, I don't want to use that. You all don't know about that yet. That says CLR. This says CLK. Okay, whose name's popping up there on my list? Tatiana, why don't you tell me?
I think she might be absent, so I don't see her.
Is she the one missing? Have I tried her twice already?
Yeah.
Okay, Oscar, tell me this one.
So would this one be a latch?
Well, maybe. What else can you tell me about it?
There's only one output, and it's not Q.
Okay, anything else?
I'm not sure, but is that an asynchronous clear?
Yep, there's an asynchronous clear. Okay, because I remember it's JK, we said we'll always assume JK unless I tell you otherwise is of the MS variety, meaning its clock is always edge triggered, even if it's drawn as level triggered. It also is edge triggered on the falling clock, even though that's not indicated anywhere here. They're indicating, this particular manufacturer is indicating that the first stage is clocked on the high part of the clock, meaning avoid changing your signal while it's high. But this is an edge triggered, so it's flip-flop. It's a JK flip-flop wired up so that it will toggle the not Q output. There is no Q, there's only an inverted Q. And as he pointed out to us correctly, it's an asynchronous clear available, meaning we can hold clear, and while we're holding it, this will not toggle. It'll just keep this at a 1. Why would it keep this signal at a 1? Anybody want to take a shot at that? Well, they would keep it at a 1 because clear is with respect to Q. Q would be a 0. So if Q is a 0, not Q has to be a 1. Okay, let's move ahead here. Hope you guys are having as much fun as I am tonight. I love this class. I like this more than going to the dentist. Okay, so let's look here and see what is on my list of many things to know and tell tonight. We looked at the 7400. Last time. Okay. And I think I went to page 7, something like that. Let's see. We were looking at the switching characteristics. That's what it was. And we looked at TPLH and TPHL, which are low to high and high to low. And they were as much as 22 nanoseconds, 15 nanoseconds. So we'll use the 22 nanoseconds for a moment here. And let's assume that I have a NAND gate, and I'm going to make up a bogus circuit here. It's not going to be real. I'm using all NAND gates here just to illustrate. And we apply a signal to these 5 wires, A, B, C, D, E, whatever they are. What is the odds of me being able to apply that signal at exactly the same instant to all of those wires? 0. There's no chance I'm going to get them all at exactly the same moment. Even if I had 2 wires, I'm not going to get exactly the same instant. However, let's assume I could. If I could, then we know the result of this particular NAND gate is going to be available here at 22 nanoseconds. If we call this 0 nanoseconds here. This guy is going to be 22 nanoseconds after that, but he actually saw this guy at 0 nanoseconds. So this guy is going to take 22 nanoseconds to get through. The signal here will change, but this guy relative to 0 is at 44 nanoseconds. This guy, of course, changes signals at 22 nanoseconds. He's going to go into this guy at 22 nano. He's going into him at 44 nano. And the result is going to come out at 66 nanoseconds. But as you can see, the pieces of it, if they're changing, may mean that what's going to happen between 22 and 44 here? Are we going to get a different signal out of this? Same thing here. Are we going to actually, up until 22 nanoseconds, is the signal here going to be different than the one we passed through because of the signal we put here? We don't know. But the system may produce bogus signals during the time that it's arriving at a final stable answer. So if we look at this and we say this circuit, put it in a box, has a 66 nanosecond propagation delay time, we know that we better not expect answers any earlier than that, from the time we change the input signals till we look at it. So let's not bother looking any sooner because we may get a bogus answer. We said last time those are called glitches. Oops. Glitches or hazards. They have subtly different meanings, but I'll let you explore that. And we could put some artificial delays in here to make it so that it's the same. For example, let's assume I had clock and I had not clock. And I wanted them to arrive over here at the same delay time because I want my 2 clocks in sync with each other. Well, I dropped down here and I add an inverter. Inverter is a lot like a NAND gate. That means this signal now is already 22 nanoseconds behind. because this guy would still be at 0. So what we might do is just stick a buffer in here just to add some artificial delay. Remember, it doesn't do any inversion or anything, so it arrives also at 22 nanoseconds. Now our clocks are in perfect sync with each other up at least until the next thing, but that's something you would worry about if you were designing a digital circuit and you'd had to operate fast. You also care because if you had two signals, you know, driving another one that looked like this, and these two times here were assumed to be at the same time, but you generated something that looked like this on the output, and that signal said launch the missile, you just created some bad times. So you have to be very, very careful that you understand the timing of your circuit and when things are going to happen. That's what sequential logic brings to the party over combinational logic. While we can arrange things to happen later in time, which is a good thing, we have to be very careful about what happens on the way to getting there. We don't want to look at this signal, at least in the launch a missile way, until we've had a stable signal and really seen what the signal is telling us. Now, there's some other signals involved when we're using a clock. So let me get this off the screen for a second here. We're going to pay particular attention right now just to this edge of the clock right here. I have another signal which I want to be latched into something on that rising edge. Now, in order to do that, my other signal can't change at exactly that point in time. If it does, I might or might not see the signal. I might latch in the wrong value. Remember, it's only going to be good as this passes through some specific voltage. TTL is about 1.5 volts that they use as a standard to say now it's flipped from one state to the other. But this is too late in time. So what I need to do is I need to back this up a little bit. And I also can't remove it right at that time because it might not have had time to see it. So I've introduced two new time periods. There's a time right in front of and a time right after the actual clock that I'm working with that I have to maintain my signal. The time right here, up until the signal, is called setup time. The time afterwards is called hold time. Now, we need to maintain those in spec. So if I go to a data sheet of the 7474, which is a D flip-flop, and I go down here to, we don't want the LS, we want this guy. We want the 7474. Very much the same sort of numbers we saw for standard TTLs. There's a 2 volts and 8 volts, 0.4, the noise margin is the same, 16 milliamps. So basically, this is good, honest TTL. However, it does tell us some things. The clock must be high for at least 30 nanoseconds. The clock must remain low for at least 37. So this sets some outside limits on the clock speed I can use. Now, I would never use it that fast, but it sets some limits. So you can't just have a little pulse and think it's going to work. If you accidentally do, it might work. So you have to be careful that you don't have noise. The amount that preset or clear, which are both inverted signals on this chip, have to remain low in order for a preset or a clear to occur, could be at least 30 nanoseconds. Now our setup time before the clock goes high is 20 nanoseconds. So we have to make our data available 20 nanoseconds in front of the rising clock in order to be able to be assured that it's going to be seen and latched. We must hold it for at least 5 nanoseconds after the clock. So those are important numbers that we need to know and need to be aware of when we're dealing with, a flip-flop. So these times we need to kind of think about, and we would put them in our planning. So we know the entire period of the clock high and clock low, has to be at least 67 nanoseconds. So let's do that. 0.000, that's milli, micro, nano. We invert that. That says about 15 megahertz is the most we'd want to operate this at. Now, there's some other things we could do with this number to make it safer, but let's just say that's the worst. Typical TTL, modern TTL today, you can push it to about 20 megahertz, and if you get all the timings right, things will work well. I would probably never push this thing much more than about 10 megahertz, even though I can see the number here will allow it to do it with those speeds. There's other considerations and other noise factors, at least in circuits, that you and I could sit down, design, and wire up, that have to do more with noise and capacitance than they do with the ultimate ability of the chip to go fast. Okay, now one other thing I wanted to show you was, there is a list in the Wikipedia of the 7400 series integrated circuits. So if we just jump down and pull the 7400s, you can see that the one we've been looking at is a 2-input NAND gate. If rather you needed a NOR gate, you could go get a 7402 chip. Of course, there's 4 of those in there. That's what the quad means, 2 inputs each. If you wanted inverters, you'd probably get a 7404, which is a hex inverter. Hex, not that it's going to be great around Halloween, but hex meaning there's 6 of them inside. And the data sheets are all listed over here. Some of these say open collector. We'll talk about those at a later time. I've actually posted one of them. I think it was a 7407, so that we'll have it online when we need it. But don't forget to look under lessons in that item. I keep updating it, adding items to it, and over time items will be removed from it. So make sure you grab a copy of anything you think you might need. So this is here. So we could go and say, okay, what the heck is a 7474? Because we just looked at the data sheet for it. And we'd see that it's a dual, meaning there's 2 of them in there. D, it's a positive edge triggered flip-flop. So we know everything we need to know about the clocking. We also see that it has an asynchronous preset and clear. So that tells us a lot. We get 2 for our money, and we would be able to hook them up to be basically 2 D latches. D flip-flops that we could use for whatever purpose we needed them for. Remember, Ds are really good if you don't need the toggle capability. If you do need the toggle capability, a JK, and particularly a JK-MS flip-flop, would be the one you'd want to go after. Okay, any questions? Okay. Let me open this up over here so I can see what I've got. We talked about a buffer register at one point, although you didn't know we were. When we did like the blocking AND, for example, up at the very top, there was something we call a register. And normally we had something like a, X3, well, it probably was X3, yeah, X2, X1, X0. And then we took those lines down into whatever the business of the circuit was. If we had AND gates, maybe, a bunch of AND gates. And then we had a second wire over here that came over. We had like an enable signal or something. Well, this thing at the top is what's called a register. And I said, this thing can remember what bits are over time. And in this case, that's exactly what we're going to use this for, is we're going to load whatever these values are, which are external values from somewhere, into these flip-flops. Notice I said sometimes they'd be flipped. Well, we put the edge trigger over here and we know it's a D flip-flop with only Q. We're actually looking at, in terms of output, these pins right here. They are the memory of whatever we latched in when the clock went high. We know clock goes high because there's no bubble on the thing. So X3 gets latched into this one when the clock goes high. X2, X1, X0. So every time the clock goes high, every instance of the clock going high, we're going to snag whatever value X has on it into these. And we're going to be able to see those values as a result of reading Q3, Q2, Q1, and Q0. Now this is very basic to understanding sequential logic. Even though there's nothing really happening sequentially here, we're simply grabbing it at a particular point in time, but that's what clocks do, right? The clock is anything that's going to allow you to synchronize something. Now, if we want to have predictable values in here that represent what X means at a particular point in time, we need to make sure that X is available. Now, how early does X have to be available relative to this clock edge? Anybody want to take a shot at answering that?
Just gotta take a wild guess. Would it be 22 nanoseconds?
Well, give that a name. What is it? What is this? 22 for this chip.
That would be the propagation delay.
Well, no, in this case, propagation delay is simply telling us how long does it take once D3 changes for Q3 to reflect that.
Ah, okay.
So propagation delay is the time between here and there. But we have to have X3 still for a certain amount of time in front of the rising edge of a clock. We just talked about it. Anybody want to take a shot at naming that?
Oh, that's the setup time. Yeah.
The setup time, right, yeah. And how long do we have to hold it after that edge?
The whole time?
Oh.
Yeah, the whole time. So we have to make sure ourselves externally, somehow we've made X stay still while the clock is ticking. And then once we tick, we know that it's going to take propagation delay time long to get to Q3. Now, we won't bring that up every time. We'll just assume we've done it right so that happens. But once we've done that, unless the clock changed, let's assume the clock never went low, or never got high, went high again, we would maintain forever whatever the X value is. And this is a very fast memory. This can be put very close to a processor, for example, and remember some data. This is even faster than cache, or one of those type of memories that you might have on a microprocessor, because this is done at digital circuit time and in the very short nanosecond ranges for this particular chip. Of course, we can make it better than that with faster flip-flops. So a buffer register is a good thing to know. It's kind of a basic digital component. It just doesn't happen to be combinational. It happens to be in the sequential logic world. So let's look at something else here. I'll move along. Got several of these. Okay, this guy looks like he's got some good stuff going on. We've seen, circuits which look somewhat complex, but this one actually, once you think about it for a couple minutes, is not really very complex. Let's just note some obvious points here. Let me grab a pencil. One of the obvious things is we have an asynchronous clear available to us. Anybody want to tell me what it would mean if I took that signal to 0?
Yeah, your Q would turn to 0.
Right. What happened is this clear is asynchronous, so immediately Q would be 0, and as long as clear was held low, it would stay at 0. Nothing else would happen. It would just hold it at 0. All the others, clock would keep ticking perhaps, but it wouldn't do anything. You could change the load signal, wouldn't do anything. Change the X's, wouldn't do anything. So an asynchronous clear overrides everything else. A synchronous clear would not, but an asynchronous clear does. Okay, so that's one thing we know. The next thing we want to notice, as if you hadn't noticed, was this little set of ands and ors here. Happens 4 times, once per bit, once for each of these bits. And it seems to be somehow controlled with this load signal. We'll get back to that. But it is the thing giving us our value. No longer is X directly connected to D. It has to go through this stuff before it gets to D. And we're still going to read our 4 signals. We're going to read Q. That will be where we take our output. We also notice that we have a clock, so if clear is not held steady, we're going to continuously take whatever this OR gate is providing us. OR gate means it's going to be giving us one of multiple things, and it looks like one of 2 things here will be given to us. The one on the left looks like it's a path that Q could get to us through. Looks like our own Q can get back to our own D. Is that true in all cases? Yeah. So our own Q can get back to us through that. Looks like X could get to us through the other side. So if I were a betting man, I'd be betting that there got to be a way I can turn one or the other of these on. And since I follow the wire, I wind up at the load signal. I'd almost be willing to bet this has something to do with that signal. Let's assume for a second that load is a 1, not load is a 0. Well, let's find out where not load is hooked, because if it's hooked to one of those AND gates, it's going to guarantee that AND gate can't be turned on. So not load is hooked here. Not load is hooked here. Not load is hooked here. Not load's finally hooked here. That means this gate can't be turned on if load is a 1. So that means the Q that was heading around to D can't get to us. However, that means all the other gates, or the ones on the right-hand side, have a 1 coming in. That means that potentially they could have a 1 on their output if X was a 1. If X is a 0, they'll have a 0 in their output. So basically, they are allowing X to pass through. So we will see X3 right here. We'll see X2 right there. X1 right here. And X0 right there. If this load is assertive. But that makes sense, because what we're trying to do is load this thing with X. So that kind of makes sense. We'll put load to be a 1, X will pass through. If the clock goes high while it's passing through, it'll be latched in, and Q will become whatever X was passed in. So all that kind of makes sense. I mean, if we could do the same thing on the other side, which obviously we can, because all we have to do, let me erase those. Make this guy a 0. That means he's a 1. So now all the ones on the left potentially can be enabled. The ones on the right, of course, are hooked to not load, which means they definitely have to be off. There's no way they could ever produce a 1 for the OR gate below. And now it's going to depend on Q. X is not even considered now because it's hooked to the rightmost one, which can't be turned on. But if Q is a 1 will pass through. Or is the 1, it sees it. and it will just maintain the current value on the next rising clock. So this seems like it's a pretty good way to do this. We have a load signal which says only move X into the register when the clock goes high and load is asserted. So you can imagine that if the only time we were interested in getting X, because it was the only time we had a value we were interested in, was that particular rising edge, we'd keep load low until about there, then we'd bring it high, we'd do the entire thing and then bring it low again. And then the only time X would have been transferred in would have been on that particular clock. And if we call this clock clock 1, clock 2, clock 3, and somewhere over here we start over again and then we raise it again when we get to clock 2, we could always make sure we only loaded what's on X during a particular clock. And that's kind of interesting. That may have some ramifications in the future, but it allows us now selectively. Remember the last picture, every clock, whatever was on D got transferred in. Now, under the control of this signal, and as long as this signal is available prior to the clock going high and holds it at least until we have made sure we had a latch, I'd probably hold it for the entire period, then we're going to be able to use that rising edge to make sure, in theory, we could stop this at 5 nanoseconds and we could make it start ahead. I forget the number now. Was it 20 nanoseconds in advance? I would probably make it be the entire period because that's the only clock we're going to see during that time anyway. Sometimes good design, is better than just going by the numbers. So this is called a controlled buffer register, and it allows us now to say, on a particular given clock, if I can determine when that is, I can put a load signal up that says pass X through to D, and on all the other clocks, recycle Q back to D so the value of Q remains the same. And also, if I ever want to just make it all zeros, I can assert clear. Anybody have a question about that? Now let's assume we did this. JK flip-flops. I'm going to wire J and K permanently high. That means they're going to toggle. Every JK is wired high. Q will toggle every time we get a, notice how they drew it here? So it's on a falling edge. So every time we get a falling edge, and internally this is probably really JK, MS flip-flops, and they're reflecting here the fact that it's happening on the falling edge. But it's really the second stage of the thing that's doing it. So the clock always is nebulous on these. Just make the assumption that it's falling edge and it's a MS flip-flop, unless I tell you otherwise. Okay, so how do we wire this up? Well, this is interesting. Instead of recycling Q back to D, we don't even have a D anymore, we're actually just using the clock. And it's going to take Q and make it be low, then high, then low, then high. And we're going to use the output of Q to be the clock of the next one. Oh, this is interesting. The output of Q to be the clock of the next one. Same thing here. And finally, we'll just, whatever Q is here, we'll just dump it out and drop it on the floor. We don't even care what it is. But we'll meter here. We'll look at Q as being where we're taking our outputs. So if I was to look at what Q is, we just forget about this guy for the moment. It would be like looking at this if I rotated it to the right. Can I do a, I probably can. Now, if I look at, this is our 555 timer, right, producing a clock for us. And we said if we put a JK flip-flop after it, it'll square it up. In this case, it looks like this signal is already pretty square, but we'll talk about it anyway. So let's write down the value we would see. We would see 0, 0, 0, 0 during this first clock, which is these first two here. We'd see 0, 0, 0, 1. We see 0, 0, 1, 0. 0, 0, 1, 1. 0, 1, 0, 0. You see what it's doing? It's counting in binary. This is flipping every one. This is flipping every other. This is flipping every fourth. This will flip every 8th, 16th, 32nd, 64th, if we had more stages. This is specifically called a ripple counter. And the idea is that once we've seen the clock, propagation delay later, we give him a clock. Propagation delay later, we give him a clock. Propagation delay later, he gets a clock. Propagation delay later, he's stable. So in spite of that, the values, if we were able to look at them, at a fairly slow, reliable pace, maybe on the rising edge of this clock, they'd be stable by that point. We'd be able to see a binary count. Now that sounds really, really useful, to be able to produce something that can produce a sequence of something. And the sequence is unique for the first 16 items, and it'll repeat. But I bet you we can make use of that somehow in order to maintain what sequence. You could think of this as we're in state number 4 right now, 0, 1, 0, 0. We're in state number 3, which would be 0, 0, 1, 1. We're in state number 15, 1, 1, 1, 1. And then notice here at 1, 1, 1, 1, it drops back to 0, 0, 0, 0. So it truly counts and it rolls around. And each stage is like a divide by 2. Each one's half the period of the other one. So if this period is 1 second, this is half a second a period. This is a quarter second, an eighth of a second. And the original guy, his period would have been a 16th of a second. Remember we talked last time that this incoming sequence here might be coming out of a 555 timer. And it might really be ugly. It might look like this. A long on time and a short off time. So it'd have a real high duty cycle that might be 90%, 95%. But the advantage of that is no matter what this is, we only are using these falling edges. Because we're using the falling edge and they're spaced equidistance apart, and we clock every other one in the next stage, even if this were irregular periods, this first stage will be symmetrical, 50% duty cycle, as will all the ones that follow. So that's a very good benefit of using a clock. And in our case, when we design our first processor, we'll probably run this at 2 kilohertz so that our machine can run at 1 kilohertz. I know it's slow. We don't have much to do. So that's something that we can think about as a really useful circuit to have, a ripple counter. And this is the timing diagram we might use with that. And again, notice that it allows us to count. It also allows us to divide. So this, if this is running at a certain speed, this is running at half that speed. Think of it the other way. If this is running at a particular speed, this is running at twice that speed. So we can use this to really home in on particular time periods. For example, in the last one where I said, let's only move the data from X into D only when it's the second clock, well, we would recognize it being the second clock because that number is 0, 0, 1. If we had the 4 phases of the clock available to us, we would know, oh, okay, here's where we need to enable, the ability of the clock, the load signal in order to make it happen. Now, clearly, we'd have to deal a little bit with the timing because we've got a rising clock rather than a falling clock in the middle, but we could certainly flip that to a not clock easily enough. Okay, let's look at another one of these guys. Again, these are just really digital components. Now, this is the same thing as the last one, except instead of this being tied to high, we tied it to a signal we're going to call count. Now, why did we do that? Well, maybe we don't want this to advance every single clock. We know if we take count and drop both these to 0, the old value of Q will be maintained. So if we make sure count is only asserted, just like we had talked about with load earlier, perhaps we'll assert count right there, we would and this is a dropping edge clock. The only dropping edge is right inside there. As long as our setup time and our hold time are long enough, count would occur only during that particular clock. The next time we have it, count's not asserted, and we would have had to make sure we had removed this before setup time because the 0 needs to be there before setup time. Picture didn't do it justice. And that would allow us then to say, okay, I want to count only every 10th count. I want to count only every 100th count. We might find a use for that sometime in the future. One of the things that comes to mind is, let's assume we had a microprocessor, and in order for it to do an instruction, it needed to have 5 clocks. Well, we could set up a clock which had a 1 here and zeros everywhere else. And then we could say, well, given what we have here, could we move that 1 over 1 position and make this a 0? And then we could always just look at which one of these 5 boxes has a 1 in it, and that would tell us what phase of the instruction we're currently executing. Sadly, this can't do that. This instead counts in binary, which we might need. For example, in a program, we might need to know what the address of the next instruction is. And those typically are numbered in sequential binary order. But we wouldn't advance that every one of these 5 steps. We'd advance it once every maybe 5 clocks, because that's when the instruction changes, because it has to do 5 little sub-things. So we'll solve this problem in a second. All we need to have is a different type of counter. How about this guy? A ring counter. Now this doesn't do 5. This does 4. The way he counts is, assume he has 0001 inside of him. When he receives a clock, he's going to do what I just said. He's going to pass that signal 1 position, whoops, well, that's okay, 1 position to the left. Next clock, he's going to pass it 1 position to the left. Next, 1 position to the left. Next clock, instead of dropping it on the floor, he's going to pass it back in again. And this pattern will be repeated endlessly. Every time he receives a clock, he'll pass a 1 along the way. And we can do that because if you notice, our Q is passed to the next guy's Q, or D, on the next clock. And it's a rising edge phenomena here. And each one does that. Even the last stage, his Q is hooked to my D. Now we do run into one problem, which is if everything had a clear, which we do, we only have 1 signal, all of these would have a 0. And if we had a 0 everywhere, on the first clock, we would shift all the zeros to the left, bringing the last one around to the beginning, but we wouldn't have anything to tell us we had a 1. So what we do instead is we take clear and we wire the first one to preset. So when we assert clear asynchronously, this will go to 0, this will go to 0, this will go to 0, this will go to 1. This is called a ring counter. A ring counter, you may also hear it sometimes called a 1-hot. Meaning, because if we were looking at our state, meaning which one is currently the hot one, there's only ever going to be 1 that's hot. Now, what would happen if we turned it on and 2 of them turned into 1s? Well, we would have problems because we'd pass those 2 1s around that ring over and over again. It's called a ring because we go around a ring with the signal. But if we had multiple 1s, that would be a problem. So as part of our startup for this, we'll always assert a not clear before we use it. The same is always almost always, I should say, true of anything involving sequential logic. There's almost always a starting state. And in our case, this is all zeros followed by a 1. We wanted our 1 hot literally to have 1 in it. Anybody have any questions about this particular counter?
Is there any particular reason that we're using not clear instead of clear as the clear input?
Almost all flip-flops have their asynchronous signals as an inverted signal. That's not our choice.
Right.
Okay.
Okay.
And so we use not clear because that's the one that would make this be asserted.
All right.
Okay. So basically what we're doing over here, we got a button, right? And we've seen it before. It has clear in one, I don't remember which way they drew it, but it had clear in one position and it had start in the other. Probably had it backwards to what I just drew. So the signal we're actually working with is clear. So when clear goes high, what does not clear do? Well, not clear was high, it goes low. And we need it to go low to push that button. So we have to hook not clear to this signal, because if we hooked clear to it, clear would always be holding it low until we said clear. That make sense?
Yep.
Okay, good. Okay, let's move ahead here. Can't make that be the right size, so I'll just make it look like that. Actually, there's probably a little button down here that I never remember. Will it do it? No. It'll shrinky dink it, but it always jumps and makes it too big. I think I gotta buy a licensed copy of this. I've done something awful now. There we go. Okay. Different way to arrange the 4. In this case, we're going to have one input that we can change. The rest of them will simply be passed to the left. Word shift. We're going to shift everything to the left, one position every time the clock goes high. It's a high going clock. Here we got a clock with high going edges. And we're going to monitor it looking at each of those positions right here. So whatever Q is, it'll be 4 bits. We're going to put D in, and D will get passed down the line. So this is spray the car. This is brush the car. This is rinse the car. I don't know. You'd never do this. Then wax the car. Probably more. When the car comes in, we pass in a 1, saying there's a car in that position. We don't know what's here right now because we have no clear on this. But after we have sprayed the car, we need to move it 1 to the left. A new car may have arrived, so there may be a 1 waiting to come in. If it does, this 1 on the clock will get moved here. This guy will get moved in here. These X's will be here, and one of the X's we had, just like the first one, will just be dropped out on the floor. Keep moving. If there's ever no car to come in, there'll be a 0. 0 gets moved in, the 2 1s get moved over, whatever was here, until we fill it up, and then whatever we put in keeps dropping out the end. So we can put a number in, shift it in, and as we go, it's going to constantly be moved 1 position to the left. Just as a pure shift register, this obviously is not as useful as if we could control which clocks we move it. Right now, we've got to keep those things going along. If you ever saw the old Lucy show where she's trying, I think it was chocolate she was trying to put in the box as the conveyor kept moving. Same thing would happen here. We would never get the thing to do what we wanted to do if we were trying to do something like a car wash. But there could be situations where you simply need a number and you're going to give it some number of clocks. Because remember, if we have a number like this and we're working in regular unsigned values and we shift it 1 position to the left and we moved in a 0, we have effectively multiplied this number by 2. That's the number 5. That's the number A, which is 10. So we could use a shift register moving left to do multiplication by powers of 2. If we were doing that, we probably would load the register with a value some other way, or maybe we simply, first 4 clock, shift in our number. 5th clock, we'd shift it 1 position to get the multiplied number, and we'd keep track of the digit we lost. Because in the case where this had started out to a 1, right, what would we have to do? This number is a D, which is a 13. When we shift it, we wind up with a 10. We lost this bit. But we can figure out a way to design a system that could use shift. I imagine we're going to get to see a shift right next. What would you think? Yes, indeedy. And shift right has simply got the behavior of dividing by 2. And notice what we did here. Our original input goes in the leftmost guy. And our Q's are always feeding the D of the guy before us. So he wraps around the end. He is where things fall out onto the ground. So our last D, when it's shifted out, it drops out here. So we're shifting to the right. Each one effectively moves, the data as though it were being shifted to the right. Now, the clock in this case, again, is an every D cycle thing. So we're going to move D every time we have one. There's no control in this, so it suffers from the same thing. But they're good examples of showing you how you might hook one up to do a shift left or a shift right operation. A more practical look would look like this. We combine kind of the buffer register notion with the shift left. And we could also make this with a shift right. We could do either. But now what we're doing is we're going to recycle Q. You see Q being recycled into our self if the leftmost guy is enabled. And he is going to be enabled either by using shift left up here or not shift left to get the other guy. So if we say shift left, the guy that's going to be enabled for us is going to be the Q going in and coming out to the next D. If we say don't shift left, we want to take Q and bring it back into our self. Now spend a couple of seconds there with your finger on your screen seeing why that does that, because remember, we're routing this Q in both cases. So think about it for a second and see if you saw this somewhere, or if I had changed the picture to shift right, what would have to be different about it? Not a lot changes. Okay, I'm sure by now you have figured it out. So let's label these. I'll label in red when shift left is a 0. So it's a 0. This is a 1. So all of the ones that this guy is hooked to are disabled right now because at least one of the inputs will be a 0. So he's got a 0 coming in. He's got a 0 coming in. Zero coming in. So just like with the logic thinking, not shift left means we don't want things to shift left. We want to recycle. So the ones will appear on all the other gates, which means they effectively could be input. So we're not shifting. What we want is a path back to our own Q. Here's one. Here's one. Here's one. And here's one. And remember again, where we're looking at the system is we're reading Q. Q is the values that we're interested in. And we have some input called DN that we may or may not be ready to shift in yet. So now, whatever Q is decides the result of this AND gate in all three cases. So it's a 1 if Q is a 1, it's a 0 if Q is a 0. In any event, it's the thing fed back to Q, or D, on every clock we see until we change shift left. Now let's swap that around. Shift left is a 1, meaning this is a 0. So all the ones that shift left is hooked to now become disabled. All the ones that shift left are hooked to become enabled. I'll draw a 1 inside of them to mean they're enabled. Meaning now that it's going to be the result of, I just marked that wrong, didn't I? Oh yeah, I'm reading both things at the same time. So he's okay. Where is he going to be able to get his data from? Well, it's got to be the previous guy's Q. It has to be a path from the previous guy Q to him. Here it is. Previous guy's Q to him. Previous guy's Q to him. And this guy, which is where we're taking our data in, has to come from the data in, which here's our path. So we can pick exactly which one of the rising edges we want our data to be transferred by making sure that this shift left right here is asserted in time for the rising edge. So it has to be asserted, and D has to be, both of them have to be stable. Whatever it was, 20 nanoseconds in front of the rising edge, remain constant for 5 nanoseconds after the rising edge. And we have to ensure that in both those cases that the clock here is long enough, which it will be because we wouldn't have designed the circuit without it being, but it's long enough that we can eat up all that 25 nanoseconds. Plus we need to eat up another 20 to handle when it goes low again. So that's kind of a tour of how those guys might be hooked up. You can imagine many more elaborate ways that all this stuff could be hooked up. Let's glaze our eyeballs on this one for a second. And kind of think through to yourself, what does this one do? Gives you a name down here. I can cut it up a little. The shift register with a broadside load. Again, this is a sequential digital component, something we would use in a sequential world because we care about the timing. So think about the features that have been added here. We could add shift right as well. It wouldn't be that difficult to add an extra AND gate ahead of the OR. But in this case, we can either take and shift a value of D in and have it shift, and the last one fall out. Remember, we're looking at Q as what we're looking at. Whether or not D goes in is a function of whether shift left is asserted. Now, alternately here, if we're not shifting left and we're not loading, we need to recycle Q. So Q has to come back in. However, if we're not shifting left, we're not putting data in for shifting left, and we want to load, we want the clock instead to affect when the X's are transferred through to their respective Ds. So we can either, and a typical use of this is beginning of the day, we clear it. Some point during the day, X's assume an interesting value. We say load, we wait for a clock. Now instead of zeros, these have the interesting value in them. We remove the clock or the load signal. We now wait till some time in the future when we want to use that interesting value. We take shift left, we cause some data to be shifted in, and everything that was preset in it moves one position to the left. You can imagine this being useful to restore the value. You've got an assembly line. In the middle of using the assembly line, you've been keeping track of where all the parts are with sensors and mostly in the software through whatever value is stored in these flip-flops. During the day, you lose power. You restore power. The flip-flops are all clear. We don't know where the parts are anymore. Yes, we do. These sensors know exactly where they are. So we shift them through into the flip-flops before we start using them, so we'll do the right thing to the parts that are on the line already. And there's many other uses where you might want to do that. I might want to change a display only when all the values are in place and ready to be changed. So I could preload, using a broadside load, all of these. And then I could shift them into position or shift them out into my interesting data field one at a time. Could do the opposite. I could also build it so it had a broadside unload. I'm not going to show you a picture of that right now because that shows on a test sometime. But we also could add shift right in addition to this, as well as a broadside unload with all this, and we'd have some other fancy flip-flop. So let's take a look here and see what the wiring is actually doing, because I think it's interesting enough that maybe we could learn something from it. If we make the data in any value, we call it X, and we have set shift left to a 1. The question in hand is going to be, if I say load as a 1, do I have a problem? Is it going to load or is it going to shift? Great test question if I had a different picture of this doing something else, right? Well, let's see what would happen if both of those are 1s. We don't care what D is because it's going to either be loaded in or it's not. If this is a 1, which one of the gates are enabled? Well, if shift left is a 1, this guy right here is a 1. He's a 1. Let's only look at the first guy. Let's just draw a dotted line for a minute that is kind of down through here or something. We might have to look at him, so we'll draw it like that. He's a 1. Load being a 1 means that the load signal, his gate, is also energized. Well, what the heck is this guy hooked to? He's hooked to the logical NOR of these two guys. Let's build a NOR gates table over here. Feel free to work ahead if you're one of those guys that wants an A in here. So far I've detected 2 of you. So a NOR says, give me an OR function but invert it. So give me a 0 anytime there's a 1 turned on. So we have the bottom case, right? We've got 2 1s going into this, making this line a 0 for the moment. Meaning that at the moment, whatever that guy's doing, he's not really doing it. Now we've got a problem. We have shift and load both asserted at the same time. That means that this guy is passing through to the OR gate and D is passing through to the OR gate. Okay. That's kind of bad because that means if either one of them is a 1, we'll pass a 1 in. So what we've just learned is load and shift left both being a 1 disallowed. So we have found the illegal condition here, that you can't say load and shift left at the same time. You know what we would probably have to do? We'd have to think about it for a while. Would it be wise just to hook those to a single signal, one which is load and the other which is shift left? Well, the problem is they can't be the inverse of each other. They have to be the same. So maybe it is wise to leave them alone and just somehow mechanically not allow anybody to push both buttons, because it doesn't make any sense to say load these at the same time you're shifting. What are we trying to do, you know? So it makes sense that one would be the other. This top line, though, is kind of interesting, because you know what it is? It's the thing that says we're neither shifting left nor loading, which is kind of what it says, nor, right? And that's interesting as well, because when we're doing a shift left, it's not shift left. When we're doing a load, we're doing it's not load. It's going to take care of the other case for us by combining the two pieces of logic. So let's first of all look at what happens on a shift left. Make that a 0. If it's a 0, shift left, well, this guy would be a 0, meaning we're only using this gate, and D would pass in, and of course the same thing happens on down the line. So that makes sense. Let's make him be the 0, him be the 1. And remember, this guy's going to stay 0 if either of these is a 1, because that's what our table tells us. So if he's a 1, that means instead of this guy is enabled. He is not. So the X passes through as it should. So that all works. The only case we didn't test was if they're both 0s. And if they're both 0s, that's the only case where this top line becomes a 1, meaning we're not shifting and we're not loading, which means these guys can't pass D through or X through, and Q gets recycled. So it works exactly as we'd want it to. The interesting observation was we've discovered the design says you can't load and shift left at the same time. But that's okay. You know, we would say the same thing, right, about set and reset. You can't reset something at the same time because the semantics make Q and not Q have the same value, and that's impossible. Okay, anybody have any other questions about that? Okay, let me go back here, and we could probably do it just with a Control F on this. And we'll go. Okay, let's shop. Let's assume we were going to go out and find a flip-flop to use in our circuit. We know a little about them right now. Notice these all have the potential in the X position to have a letter like L, LS, or S, or HCT, or A, ALS, some of the other kind of sub-architectures of the 7400 series. We're working with the one that has nothing there. It's basically the standard, the original series. But if we look, the 7467 is what's called an AND gated JK master slave flip-flop, or MS flip-flop, with an asynchronous preset and clear. It also tells us that it's an improved one of these. So as time goes along, they may develop new numbers and things. Even though the number's lower, it may have been a device for which there was a standard family, but not an L family device that they later improved upon. If we look at the data sheet, hopefully they'll have a data sheet. Page 164. Might have been easier to find one that was a standard data sheet. Now we'll just look for it. We'll look for it next time we find one. I want to show you what the AND gated part means. Now here's a 7468. The one we were looking at a while ago was a 7474. Notice this only comes in the L version, but it's a dual JK flip-flop. This only had one in it. There's a dual JK flip-flop with an asynchronous clear. Notice there's only a clear, there's no preset. It's also a JK. Here's an 89 or 69. This has an asynchronous preset. Plus, see, there's two of them in there. They share a clock and a clear. So each one has its own preset, but they share a clock and a clear. That could be useful in a design as well. Here's an AND gated one. This is a Texas Instrument data sheet. Let's look at it. Don't be afraid to go look these up and look at the, it's probably a book reader. This machine I'm on, does it have that? Probably doesn't. Okay. Here's one that's AND OR gated. What they're basically doing is they're putting some logic in the path so you don't have to put it externally. Very often you'll use this. Now notice here, RS master slave flip-flop. This is one that's not a JK. It does not have the toggle notion to it. Finally, a D. This is the first good D that we've seen. This is the one that we were looking at the data sheet for. And we have a data sheet for it, but it doesn't have any leading logic. So many of these, and there's, 81 of them in here, different flip-flops in this family. And we're only looking at the ones that are, I think, less than 100. No, we're looking at the whole list. Here's one that's negative edge triggered that's not an MS flip-flop. So you might have a need for that in a design. A lot of these are old, outdated, and a lot of them have families that are a lot faster, so we would not be too concerned about them. Let me find that again. What is this one? And let me look at my sheet for a second here. Yeah, it's on page 4. Okay, this again, if you use these data sheets, be careful because this is for multiple devices. If I were to ask you specifically about an LS, if you look at the column headings, these are not the LSs. If I ask you specifically about military, it's this column, not that column. Make that a little bigger so you can see it. Okay, what I'm interested in here were some of the numbers and things we had looked at before, just to make sure you see how to do this. If I ask you for this, what are the TTL numbers for this? You know, remember for a gate, this is a little more complex internally. If you saw the picture up here, that's a lot more stuff going on. And so you would expect maybe some of the delays and things in this would be a little more exaggerated than they are for the standard family. Here's our supply voltage, high level input, low level input, and you'll notice they're the same as they were for the standard family, as I mentioned earlier. Here's the output they're going to give us, and the 0.4 where the output here is out of the chip, 16 milliamps into the chip. So it's the same relative quantities we had. But when we get down here for these that are synchronous, or there are going to be chips that have to do with sequential data, we get some extra data. The width of a pulse, we talked about those. We talked about the setup time, the hold time. Now, down here, as we move much further down to the switching characteristics, almost to the bottom of the page, you'll see here's the frequency max. You wouldn't see this for standard logic. You see this for anything that has a clock. It's guaranteed that the worst it can do, let's say you pick a really bad one out of the box that's fully functional but meets spec, it would be able to do 15 megahertz. So while I could design it to do 25, one I pick out of the box might only do 15. So I would have to very carefully check to make sure it didn't. That's why I always use 10. It's in this ballpark, but it's got a little more safety built in. Same thing in terms of other test conditions. When they ran these tests, they hooked up, and there's a picture further in this diagram of how, actually I think it may even be in the other data sheet, of the load resistor and the capacitance of the load they're using. If these change dramatically, then these times, which are our pulse times that we saw earlier, could change. So the propagation from low to high, if it's caused by preset or clear, is going to take as much as 40 nanoseconds. Now, that's going from high to low. If it was going from low to high, only as high as 25. But I would plan for the 40. That's one of the numbers. In terms of propagation delay, of course it's longer than a gate. We've got more stuff to go through. Again, if it's caused by the clock, not preset or clear, it could take different amounts of time. Again, they estimate it, but they give you some typical times. Usually, chips meet the usual, but under extremes, you might find it, yes, having to go to those other times that we have there. So that's one of the things, and I'd want you to be able to look these up in here. So if I had asked you, for example, tell me about the S, here it is, and I said military grade, or here it is. What's the pulse width duration? Well, it's got to be at least 6 and for clock high, and it's 7.3 for low. What's the setup time? Well, it's only 3 nanoseconds here. It's a little better chip, right? So what if I ask you about the maximum frequency? Look at this. Could go to 110 megahertz typically. Don't go lower than 70. What's a better chip? And that's because of the S, not because of the military. Notice for these frequencies down here, they are not qualified by anything except they happen to be on this page for the S chips. Because on each page you've got your own set of max frequency. If I was using an LS, LS can go 25 to 33, a little faster. Or is this the LS? Yeah, which is a low power, has something called a Schottky transistor in it. And without explaining that in detail, which I'm not going to do today, we will later, but it just means the transistor can switch faster, as can the S, which can switch even faster because it doesn't also require low power. Okay, I think that's going to be close enough. Does anybody have any questions before we go for the day? I will post that set of slides I showed you on the lessons area of Blackboard as soon as I get a chance after class tonight. And, you know, I will see you guys, on Wednesday? I think last week I said I'd see you on Monday or something, but actually, what is today? Is it Monday or Wednesday? I got to sort that out sometime.
Monday, Professor.
Today's Monday. Okay, then I'll see you guys Wednesday. So you guys have a good one until then.
See you.